Pre-calculus students, welcome to today's 9.6 notes. As you smoothly groove with the help of Boys to Men into this lesson, let's get started. We're going to talk about counting principles today. Now I can assure you the principles we're going to look at are slightly more advanced than those counting principles you learned back in the pre-K days. We're not just going to have you count numbers. We're going to do some things that are a little more advanced. So let's talk about selecting pairs of numbers at random. Suppose that tiles numbered 1 through 10 are placed in a bag. One tile is drawn and placed back in the bag. Then the second number is drawn from the same bag. How many different ways can a sum of 16 be obtained? Well, the only way we can get 16 is if the first number is at least 6, because the largest number is 10. So we could get 6, 7, 8, 9, or 10. And then that would be coupled with the numbers 10, 9, 8, 7, and 6 from the second draw. So that would give us a total of 5 combinations that would sum to 16. Now on number 2, it's really a similar problem to what we see on number 1, the big change being that we're not replacing the tile. That's a key difference, because effectively not replacing the tile, what it does is it eliminates one of those 5 possibilities. You can see it. It's the one with 2 8s. We can't draw 8 twice because we're keeping the tile out of the bag. The other 4, though, would all be fine. Okay, so let's look at number 3. This time a computer is randomly generating integers from 1 through 20 without repetition. Determine the number of ways to generate multiples of 3. Now I underlined without repetition. Again, that's a key thing at some point. It's something you have to consider. When we talk about multiples of 3, we're talking about numbers like 3, 6, 9, 12, 15, and 18. That would give us a grand total of 6 possibilities. 6 possibilities for multiples of 3. Now again, on this one we're only drawing 1, so the repetition isn't really important. On B, for prime numbers, remember 1 is not prime. That's the trick here. 2, 3, 5, 7, 11, 13, 17, and 19 gives us 8 total possibilities. We're perfect squares. We'd be talking 1, 4, 9, and 16, so we have 4 options there. And then finally on part D, 2 numbers that sum to 17. This is a lot like what we saw on number 1. Again, remember without repetition, but we would start with a 1 and a 16, and then we'd have a 2 and a 15, and this pattern would continue on until at the end when we got 16 and 1. That gives us a grand total of 16 possibilities. Alright, moving ahead to the next page, the fundamental counting principle. If E1 and E2 are 2 distinct events, the first event, E sub 1, can occur in M sub 1 different ways. After E1 has occurred, E2 can occur in M2 different ways. The number of ways the 2 events can occur is M1 times M2. The key to this, folks, is that we're talking about 2 events leading to multiplication when we're saying what's the probability of both. And I said probability, I misspoke. That would be the number of ways. Now, how many different ways can 6 boys and 6 girls line up? This is an interesting question because it doesn't seem like it'd be this huge of a number, but it's 12 people. So you have to consider that you could have 12 people lined up first, then you could have 11, then 10, then 9, then 8, and so on. And you end up with this massive number of 12 factorial, which is about 479 million and some change. Lots of possibilities. I know that doesn't seem right. Try it if you want to. It might take you a while to demonstrate this in real life, though. Now, with just one simple limitation, that all the girls are lining up before the boys, that changes this number pretty significantly, because we have to consider it as 2 problems. The first would be girls. That would be 6 factorial. The girls could line up that many ways, and then the boys could line up 6 factorial ways. And so it's still a large number that you get here, but you multiply 6 factorial and 6 factorial, you get about 518,000 and some change. And so the idea here is, even though that's still a large number, it's about 1/100th the size, 1/1000th the size of without that limitation. All right, license plates in Kansas have 3 numbers, then 3 letters. How many distinct plates can be produced? So I like to think of this problem simply 1 digit at a time. So I usually draw some little boxes to represent each of the places. Now some of you may be above the boxes, that's fine. And I just think of it this way: that first box could be any of the numbers 0 through 9, so we have 10 options there, and that would hold true on the other 2 places as well. But then when we get to the last 3 boxes, we now have letters, so there are 26 options. And when we want to know the total possibilities, I'm doing 10 times 10 times 10 times 26 times 26 times 26, and we get a pretty significant number here: 17,576,000. And it should be pointed out that's significantly more than the population of Kansas. So if we stick with that method, we should have enough plates, even though some of them we don't use for obvious reasons. Okay, how many 4-digit numbers are formed under each condition? The lead digit is not 0. That would be, that would mean our first digit could be 9, and then we have 9 possibilities. The other 3, we could have 10 possibilities for each, so we'd get 9,000 options. For part B, again, we start with 9, but then there's no repetition, so the second digit has to be only 9 options because 1's already been used, and then we'd have 8, then we'd only have 7 remaining, and so that gives us 4,536 possibilities. Now the last one, the lead digit is not 0. We've seen that, so we start with a 9, and then the number is even. Sometimes this confuses people. Remember, an even number has nothing to do with the first, second, or third digit. It's only the last digit that matters. And so we end up with 4,500 options, which kind of makes sense if you think about it. Okay, local telephone numbers have 7 digits. The first cannot be a 0 or 1. Find the the number of distinct telephone numbers. Since we eliminate 0 and 1, we know we have 8 options for that first digit. Nothing else is restricted, so it's all 10s after that. Now we do know there are some actual other limitations, like you can't have a number start with 911. That would be kind of silly. So there are some others, but ignoring those kind of things, we have 8 million possibilities. All right, a permutation of n different elements is an ordering of the elements such that one element is first, one is second, one is third, and so on. In short, order matters. How many different permutations are possible for the letters A, B, C, D, E, and F? Well, the first number the first spot, you could have 6 possibilities. It could be A, B, C, D, E, or F. And then you'd have 5 left, then 4, then 3, then 2, then 1. Another way of saying that is 6 factorial, or just simply 720. So there it is, 6 factorial. That's where factorials come into play. How many different ways could you organize those 6 letters? Now on 9, we have 8 horses running, but we're only considering win, place, and show. That's first, second, and third place for you non-gamblers. So we would have 8 possible winners. We could have, once we have a winner, we only have 7 options left for second place and 6 options left for third place. That gives us 336 permutations. Now, we have a little formula, NPR, the number of permutations of n elements taken r at a time. You can see the formula there. It comes in handy. So we can use it in the scenarios that we see here. So on number 8, that was a 6p6. We have 6 items that we're arranging in 6 ways. And so what we have going on there is 6 factorial divided by 0 factorial, which would give us 720. Whereas on number 9, we have 8 horses. We're trying to arrange 3 of them. And so that's an 8p3 situation. And again, you can do this simplification by hand, or you do have the option of punching this in the calculator. You may have seen that NPR option when you look for NCR. Okay, a little slightly different topic, distinguishable permutations. Suppose that a set of n objects has n1 of one kind of object, n2 of a second, n3 of a third, and so on. So the total number is if you add all these events together. In this case, the distinguishable permutations, you can see the formula there. You take the total number of events and then divide it by the ones that repeat, factorial. All right, so let's do this with the word banana. You can see I've underlined some repetitious letters. I know that the word banana has a total of 6 letters, so I'm going to put 6 factorial in the numerator. The denominator, we have 2 n's and we have 3 a's, so I'm going to put 3 factorial and 2 factorial. That would cover the repetition of letters. And then we can simplify this. It's basically 4 times 5 times 6 divided by 2, which would be 60. So if you wrote the letters of the word banana in a different order, there'd be 60 ways you could do it. Why don't you guys do number 11 on your own? All right, you can see what I've got on number 11, 1,663,200 distinguishable ways that those letters from the word Albuquerque can be arranged. All right, when you count the number of possible permutations of a set of elements, orders is important. With combinations, however, orders not relevant. For example, the set ABC is equivalent to the set CAB. And how many different ways can the letters be chosen from A, B, C, D, and E? So I'm going to start organizing a list. We've got A, B, and C, A, B, and D, and so on. Why don't you guys finish completing this list? There are several options here, and I'm going to skip ahead. And here is my last one, C and D and E. You can see those. That's 10 ways. So 10 ways we could have the letters A, B, C, D, and E. Remember, it's not including order, just simply which letters you have. Now, this is an NCR situation. We have seen NCR before, but this is a place where it would be used. Again, it's where order doesn't matter. So we could have done number 12 as a 5C3 problem. Now in this case, I'm not sure that 10 ways is all that complicated to solve, but when we get to larger numbers, using notation like the NCR is really helpful because you don't want to have to list 2 million items or possibilities.
What we're looking at here, we have a standard set of cards that has 52 cards in it. How many different 5-card poker hands are possible? Now we know the order of a poker hand isn't important. You can rearrange them freely within your hand. So what we have going on here is a group of 52 where we are choosing just simply 5. Okay, 52 C5. This is a pretty large number, 2,598,960. So we have what, 2.5 million different possibilities for hands when playing poker. All right, the U.S. Senate has a committee with 14 members with 100 senators. How many different committees are possible? Okay, again, within this group, the 14 members can be from any particular order. So this is, again, a committee situation. We're picking 14 from 100, so it's 100 C14. This is a really large number. I'm getting about 4.42 times 10 to the 16th power. Again, really big number. If we were choosing, if the order did matter here, that number would get even larger. But in this case, 4.42 times 10 to the 16th is the number of possibilities we're looking at. Okay, and then our final question. In the Louisiana Lotto game, a player chooses 6 distinct numbers from 1 to 40. And how many ways can a player select the 6 numbers? So the word distinct is important. That means there can't be repetition. That means essentially we've got 40 numbers that we can pick from, and we're choosing 6. Again, order would not be important in this situation. 40 C6 is about 3.8 million, 3,838,380. That is the end of our notes for today. I hope I still have a job tomorrow, seeing that my notes are on gambling and politics. I'm sure to offend just about everyone.